Hi everyone, this is Elisa Baum, GridGain's Director of Product Marketing. We'll begin in just a moment, but first I need to conduct a little bit of housekeeping. If you could please raise your hand using the hand icon located in the GoToWebinar control panel and let me know that you can hear me, that would be very appreciated. And let me see here. Does everybody hear me? Good, I see hands. Great. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, and I know you will, please enter them in the questions field within the control panel. At the end of the webinar, we will take time to answer as many questions as possible, and those that aren't addressed will be answered in a follow-up blog entry on GridGain's blog. In addition, I'll make sure that you have a link to both the recording and the slides within 48 hours after the event. So with that said, I'd like to thank you for attending today's webinar, Tuning Apache Ignite for Optimal Performance. It's being presented by GridGain lead architect, Valentin Kolichenko. And with that, I will turn the floor over to Val. Go ahead there, Val.
All right. Thank you, Elisa. Hello, everyone. My name is Valentin, and I'm lead architect at GridGain Systems, and I'm also active committer and PMC member of Apache Ignite project. And in addition to that, at GridGain, I'm heavily involved in customer support and professional services. So I have a lot of experience in how Apache Ignite and GridGain are used in real time, in real life use cases, and how the performance can be solved in different situations. And I will try to share some of this experience today with you. All right, so let's talk a bit about our agenda today. So for those who is not familiar with the Apache Ignite project, I will give you a short overview. Then I will talk about we'll give you the overview of different performance problems and different performance bottlenecks that you can have in your applications, and give general advices of how you should approach that. And then I will move to actual techniques of about how you can approach the performance issues when you're using Ignite, when you're developing applications with Apache Ignite. I will talk about basic cache operations. Then I will talk about data loading. I will also cover a very important topic, which is affinity colocation. And then I will talk about tuning of SQL queries and as well as JVM tuning. And at the end, I will show you the quick live coding demo showing some features of affinity colocation in Ignite. And then I will answer your questions if you have any. All right, let's start. So the Apache Ignite is actually an in-memory data fabric. Data fabric here actually means that there is a set of components that can be used independently for different purposes, for different use cases that you have in your application. But at the same time, all these components are highly integrated with each other. Like as an example, there is a data grid component, which is probably one of the main components and most widely used components, which allows you to store your data within the data fabric. And then there is a compute grid, which allows you to execute distributed computations, like MapReduce or fork join tasks, for example. And depending on your use case, you can use only one of these components, only data grid or only compute grid, or you can use both. And like combination of these two modules. And this is usually used in case your computation tasks are going to work with the data, like to process the data that you have in the data grid. And there is a lot of different features in the API allowing, making this integration very easy for you. But like in any case, whatever you do, you will have like a single cluster of nodes, which actually forms this kind of a layer between your data sources, which can be different data sources like relational databases, NoSQL databases, or Hadoop, or basically anything else, and your applications. So in a nutshell, this layer fetches your data into memory. for the fast access, and then provides multiple APIs to access and process this data. Ignite natively supports Java, .NET, and C++ APIs, but there is also rich SQL support, including JDBC and ODBC drivers, so that you can actually use Ignite from other platforms like Python, PHP, and so on. And in addition, there is a separate module for Hadoop acceleration. So basically, it's a plugin for Hadoop, which Hadoop can use to execute existing MapReduce jobs, so that you can speed up these jobs without any code changes. And on top of that, there is a memory file system, which also can be used as a caching layer for these jobs. Caching layer like between HDFS and these Hadoop MapReduce jobs that you are executing on the fabric. And there are other components like clustering, which is basically responsible for making sure that nodes properly discover each other and form a single topology, streaming, and other components. But the core component of the data grid, of the data fabric, is data grid. This is actually a distributed key value storage, and the storage is reliable, meaning that you can have one or more backups copy for each entry for redundancy. So in case you lose one or more nodes, you actually do not lose any data. And it also provides very strong consistency guarantees, including ACID transactions. So like with any relational database, you can start a transaction, update multiple entries within this transaction, and then Ignite will make sure that either all of them are updated successfully or all of them are rolled back if something goes wrong, if transaction is rolled back. And in addition, there is also, like in addition to the basic key value API, which is basically similar to like concurrent map, there is rich NC99 compliant SQL support. Like all different SQL expressions like group by, order by, joins, and so on are supported. And there's also advanced indexing capabilities as well. But actually the main advantage of the data grid is, of course, that the data is stored in memory, which give you fast access to this data, high performance, and high scalability. So having said all that, Ignite is actually all about performance, and actually performance and scalability is what this product provides. But I would actually encourage you to keep in mind that there is no silver bullet, and although Ignite is a very powerful tool, creating a fast application using this tool can be pretty challenging and can require some specific knowledge and skills. And that's what I'm going to talk about today. So like, let's imagine that you created your application. You defined some performance criteria. So you have some metrics that you measure in your benchmarks. You have some SLAs for these metrics, and so on. And then you run the benchmark, but the result is still unacceptable. So what are your next steps? And actually, one of the like first very important steps is to try to isolate this issue. Meaning that you have to understand which component of your system is causing this performance degradation. So which component of the system is actual bottleneck. And here we can like kind of distinguish several layers of the application where you can have such a bottleneck, where such a bottleneck can occur. The first one is the application layer. This is your actual application code, including all your dependencies that you're using. Bottlenecks here are usually caused by incorrect or ineffective code. Like as an example, if you're using Ignite and you're using it incorrectly, in some cases it can even cause performance degradation instead of performance improvement. And if you need to make sure that you do everything correctly and you do everything in an efficient way, so that application works fast. Then there is a JVM layer. So Ignite is a Java application, and therefore it runs within the JVM, and everything that applies to any Java application, applies to Ignite as well. And usually problems on the JVM layer are somehow related to memory. So you can just have insufficient memory for your data, which can cause out-of-memory errors or high CPU utilization by GC threads or issues like that. Or you can have long GC pauses and so on. Then there is a system layer, which is actually your operating system. And bottlenecks here are usually associated with things like CPU saturation, memory swapping into disk, disk and network I/O problems because it's not tuned enough and stuff like that. And then finally, there is a hardware layer, which is actually your hardware where you're running your application. It's like if you have bare metal servers, or you have virtual machines or AWS, or virtual machines in some private cloud, like all these different types of hardware can give you very different results on the same with the same application, with the same data, and with the same settings. So having said that, you should always go from top to bottom when analyzing performance issue. So you should start with the application layer, try to find out if there is any issue in the actual code of your application, and if you are confident that there is no problems there, you can go down to JVM layer, system layer, and so on. In my experience, most of the problems are on either application layer or JVM layer. Like system layer and hardware layer become important in big, like very high loaded systems. And having said that, today I will talk mostly about the application layer and the JVM layer. Okay, so let's actually move on to like actual techniques of how you can work on performance improvements when working with Apache Ignite and when developing applications with Apache Ignite. And I will mostly talk about data grid because this is the most widely used component of Apache Ignite, and performance there is very, very important. So let's start with the basic cache operations. So basic cache operations are like get, put, and remove. These operations allow you to manipulate single entries, like get reads particular entry by a key you provide and fetches this entry to the client. Put method updates this entry or inserts a new one and removes the existing entry from the cache. And when you think about performance of such operations, it's very important to understand what is your goal and what metric you want to improve. Because basically there are two main metrics here, latency and throughput, where latency is time of individual operation measured in seconds, or milliseconds, microseconds, nanoseconds, while throughput is the number of executed operations per period of time. Usually it's measured in operations per second. And the problem here is that they often go against each other. And this actually happens because when you increase number of concurrent operations on the same amount of resources, you improve throughput, but the latency will usually go up, and you will get higher latencies. And the only effective way to bring the latencies back down in this case is to scale out. Basically when you add more nodes to your cluster, you split the load, you split the throughput across these nodes, and since the load per node, the number of operations executed concurrently on each node decreases, you get higher latency. But as for throughput use cases, you can also scale out. Scaling out happens in majority of use cases actually. I mean, if you have performance problems, adding more nodes is one of the things to try, and in many cases it gives very good improvement right away. But for use cases where throughput is more important than latency, there is another very powerful tool that you should be aware of, and this tool is batching. So basically, when you group operations in batches, you decrease the number of network messages you have in your system, and therefore you improve the throughput. But keep in mind that usually it's not good for latency, because the first operation in batch will wait for the last operation in the same batch. And the latency of this first operation in the batch will be very, very high. So this is actually, batching is usually should be used in case you're not really care about the latency of individual update or individual read, but you want your system to process as many operations as possible in the period of time. In Ignite, there is almost every cache operation has a batched sibling. Like for get, we have a getAll method. For put, we have putAll, and so on. In this case, if you use these methods, you will have to create batches manually. So like getAll basically gets the set of keys. putAll gets a map of values of entries that you want to update, and so on. But in addition to that, Ignite provides a very cool feature called Ignite Data Streamer, which actually gives you the automatic batching. And an example on the bottom of the slide, you can see how the data streamer can be used. So it's very simple. Basically, you create a data streamer using the Ignite API for a particular cache, providing the cache name. And then for each entry you want to save in this cache, you call the addData method. And note that this addData method is actually asynchronous. It does not actually save this entry in the cache. It does not do any network operations. It only adds this entry into the local queue within the data streamer, and it's up to data streamer to decide when this queue will be flushed. And there are several parameters that you can configure, like the size of the batch, or you can have a timeout after which the queue will be flushed anyway, even if it's not full yet, and several others. All right. So another use case where the Ignite data streamer can be used is bulk loading of large amounts of data. So very often, this is the very first task user has to accomplish, and this task can be pretty challenging sometimes. Ignite has basically two different approaches that you can use for this task, and I have both illustrated here on the pictures at the bottom of the slide. The first approach, which is shown on the left, uses Ignite data streamer. So there is a client node designated for this data loading process. It loads the data from the table or tables in your database, and then uses the Ignite data streamer to stream all these rows into the server nodes. But the problem here is that there is, first of all, it's a single point of failure. So if this client node fails, you have to restart the loading process. And also it can be a bottleneck, because basically this client node transfers all the data from the database, and then it has to transfer the same amount of data to the cluster. So why not load the data directly from server side? And this is also possible. There is a special cache store interface, which is actually a pluggable component that you can use to customize the logic of integration with the persistent storage, and you will use it if you want to utilize write-through or read-through. But in addition, it also allows you to load data from the database into cache, like bulk load a large amount of data. There is a special method for that called load cache. And in this case, the server nodes will load the data from the database directly, but note that in this case, each node will have to load all the rows from the table. Like if you have 300 rows in this table, each node will fetch all 300 rows. And then it will locally iterate through the whole data set and filter out the data that has to be stored locally and discard everything else. However, there is a pretty interesting trick that you can use to speed up the process when you use the cache store. So you probably noticed that, I mean, as I already mentioned, there is a big disadvantage of this approach, that you load all the data on each node, which can seriously overload your network, especially if there are a lot of nodes. Like, probably it's not a problem when there are only 3 nodes, but if you have 100 nodes, it can be a big problem. So and it looks like a lot of redundant work, and it's actually true. But there is a reason for that. The problem here is that generally the cache store implementation does not know how to select only those rows that will be then stored on local node. And so the cache store is forced to load everything and then filter out locally. And to overcome this problem, you can use like another approach that we call partition-aware data loading approach. So on this picture, like imagine you have 3 nodes and 9 partitions, and partitions are distributed across nodes like shown here: 0, 1, 2 on node 1, 3, 4, 5 on node 2, 6, 7, 8 on node 3. And what we do here is we actually add a special partition ID column into the table in the database and pre-calculate this column. So this mapping between the key and partition ID never changes, it's constant. So you can pre-calculate this the partition ID for each ID and save it into this column. And then when the actual data loading happens, node 1 will not select everything from the table, but will select only rows which have 0, 1, or 2 as partition ID. And node 2 will load 3, 4, 5, node 3 will load 6, 7, 8. And in this case, if you have 300 rows in a table, each node will load approximately 100 rows instead of loading everything. So they will actually split, the loading process will be split across all the nodes that we have in topology. And this is a very good approach from performance standpoint, and in many cases it's the best one from performance standpoint, but this requires database schema change, which is not always possible. All right, now I would like to talk about affinity collocation. Affinity collocation is actually a very important topic and a very important feature available in Ignite, because in many cases it can give you like orders of magnitude improvement when it's properly used. And this is probably one of the first things you should take a look at when you create your application, when you create your data model for the data grid, and when you actually defining the architecture of your future application. So basically, let me talk about affinity, about what is affinity, so that you properly understand that. So affinity is actually a mapping between the cache keys that you store in the data grid and nodes where this key are stored. So for each cache key, like when you do a put for a particular key, you have to be able to know on which node this key will be stored. And in Ignite, this is implemented as affinity function, which is actually a stateless hash function that independently returns consistent results on all nodes. What this means is that actually we do not store this mapping anywhere. We don't have anything like name node because it will blow up your memory and it will be a single point of failure, so we don't want to do this. So instead we use this stateless function, and whenever it's called, whenever Ignite wants to like send a message to a particular node where the key is stored, like for example send an update request to update the entry, it will actually call this function for this key and get the and it will get the information about the node where this key is stored. And another important concept here is affinity key, because actually the cache key directly is not used for this mapping. The affinity function takes the affinity key, and the cache key is first converted into affinity key, and then the affinity function takes the affinity key to get the partition number and the node. And the difference here, the main difference here, is that affinity key, unlike cache key, doesn't have to be unique. So you can have the same affinity key for multiple entries, and this will force Ignite to store all these entries with the same affinity key on the same node. Like for example, you have imagine you have an employee cache. So this is shown like on the example at the bottom. So imagine you have an employee cache with employee objects, and in this case, and every employee is actually belongs to some organization, and you have and you know the organization ID this employee belongs to. So in this case, you will create a special employee key class, which will be used as a key, as a cache key, but there will be actually the ID, which will be actually used as a cache key. So the equals method and hashcode method of the employee key will be based on this ID field, and this has to be unique for all employees. So each employee has to have different ID, and additionally you have the organization ID field, which will be used as affinity key. And here we put the special affinity key mapped annotation, which actually tells Ignite that this field has to be used as affinity key. And all employees with the same organization ID will be stored on the same node. This can give you a lot of improvement. I mean, for example, if you want to then run some computation that processes, calculates the average for this employee, for this organization, like average salary of all employees in this organization, for example, you can send a computation to that node. You will have all the employees locally, and you will execute the computation really fast. So this is so basically you can collocate both data with data when you have like organization class and employee class, and you can have the organization with all its employees on the same node. And you can also collocate computations with data as well, so that you can send a closure or a computational job to the particular node where particular affinity key is stored. And you can think about affinity collocation as about a different approach to development in distributed systems, opposed to like traditional client-server architecture. Because with a simple client-server, like any cache operation, read or update will imply a network trip, and you will also have to send the whole value across the network at least once. Like on this picture, if you want to process the data, like you want to get some data from one of the data nodes, then you want to do some processing and save it back, you will send this value through the network between data node and the processing node 2 times. And if the value is pretty big, this will take like a lot of time. But with the affinity collocation approach, we actually send the lightweight computations to the data, not the other way around, which seriously reduces network traffic, and which is very, very good from performance standpoint. Because since we're in memory is very fast, but network is very slow. So if you add a lot of network, you actually often lose all the advantages of the in-memory computing. So you should always try to reduce the amount of network communication. And affinity collocation helps you with that. And there are several APIs in Ignite allowing you to do that, and I will actually show them later in the demo. All right, so let's talk a bit about SQL queries and tuning of SQL queries. So SQL capabilities are actually really huge in general and in Ignite in particular, and therefore there are lots of techniques for improving its performance. But the cornerstone here is, of course, indexing. Like whenever you want to select any data filtered by a particular field, you will most likely will want to create an index for this field to avoid the full scan of the table. And Ignite actually has full indexing support. So query optimization with Ignite doesn't differ much from the similar process like with a traditional relational database. Meaning that the main goal here is to find a combination of indexes that will give you the best performance. Note that usually it doesn't make sense to index like every field that you have in your tables because it will only blow up your memory, because each index has to be stored somewhere. And there are several cases when indexes are not really used. Like some fields are not used in where clauses, so you don't use them for in your conditions. So it doesn't really need it to have these fields indexed. It will not give you anything. There are cases when it's actually better to create a group index for multiple of fields instead of creating a single, like individual index on all these fields. And like so on. There are a lot of different cases when you don't need to index a field, but indexing in general really helps you to improve performance of SQL queries. And the first thing to figure this out, to find this set of indexes you want to use, is to run the explain statement to get the execution plan. In Ignite, it's done with this explain statement. Actually, you just prepend your query with the special explain keyword and then run it. And instead of actually executing the query, Ignite will give you the execution plan that it uses for this query. And the execution plan shows you like a lot of information about how the query is executed, what is the order of joins, if there are any, which indices are used for this query and which are not used, and so on and so forth. And basically you have a lot of like all the information about how query is executed, which you can analyze to find out is there any way to improve the speed of this particular query. And for your convenience, there are several tools that you can use. First one is like used for debugging. The first tool I want to mention is GridGain Web Console. You can find it both on the Apache Ignite and GridGain websites, and it's actually a web application for monitoring and management of Ignite cluster. But in addition to that, it allows you to run SQL queries to get the execution plan for your queries, to browse your data and browse your metadata and so on. Very beautiful, powerful tool, so check it out. There is also H2 debug console. It's kind of a Ignite uses H2 under the hood for query execution. And you can use H2 debug console to actually connect directly to the H2 database running inside the node. And this gives you some capabilities for low-level debugging of your queries. And at the bottom, there is the link to our documentation page, which you can check out to get all this information I just mentioned, and with some more details about how to run H2 console, for example, some examples how to run explain statements, and so on and so forth. And in addition to all that, I would also like to emphasize the importance of collocation for SQL queries as well. So basically, when you join two tables, you should always try to collocate them. Like remember our organization and employee example. If you want to join organization with employee by organization ID, we want to have all the data for this organization on the same node, all the joint data on the same node, because otherwise Ignite will have to reshuffle the data, transfer it across that network, which will reduce the performance. Ignite actually does support both collocated and non-collocated modes for joins, so you actually don't have to collocate to get correct result, but from performance standpoint, you should always try to collocate as much as possible. So, and use like non-collocated mode only as a last resort. This is usually useful for like analytical use cases where it's hard to predict all possible joins that will happen in the system. But at the same time, you can afford that some of your queries, like 10% of the queries, for example, are slower than others, while 90% of the queries are working in fully collocated mode, and they are very, very fast. So collocation is important when you're running SQL queries as well, not only when you're running like using basic cache APIs or using computations. So, and the last but not least topic I want to cover is JVM tuning. So, like most of the issues that you will have on the JVM level will be related to memory management in Java. And when you will develop and test your applications, you will very likely get some out-of-memory errors first, some GC pauses, and other bad things that will slow you down or will make system unstable. And here are several recommendations about how you can make sure that such issues almost never happen or never happen. The first one, never use, try to avoid large heap sizes. The problem is that if the allocated heap is very large, like more than 16 gigabytes or so, you will most likely eventually get a full garbage collection that will take a lot of time because there are a lot of objects, because the heap is very, very big. To deal with this, Ignite provides an option to store data in off-heap memory. So basically, this is still RAM. It's pointer away from your application, and it's still very fast. But Ignite manages this memory directly, manually. So JVM is not aware of it, and garbage collector is not aware of this memory. And even if you have like a big box with hundreds of gigabytes of RAM, you can create a small JVM, like 8 gigabytes, 10 gigabytes, or something like that, and move the rest of your data, actual data that you store in the cache, to the off-heap memory. Second advice, always use G1 or CMS collectors. CMS is basically default from starting with Java 7. G1 is default starting with Java 8, 9, if I'm not mistaken. But in any case, like any older garbage collector will be very bad from performance standpoint because they frequently go into log the world collections, which are really unacceptable in distributed system because it's not only degrade your performance, it also make your system unstable. If like a node goes into log the world collection, it's unresponsive for significant period of time, and other nodes will just consider this node to be failed and remove it from topology. Another advice is always collect GC, garbage collection logs. I would just recommend to enable them in all your environments. So if something happens, you always have enough information to analyze what actually happened. Because there is a frequent situation when you already had like GC issue, but you don't have any logs and you don't have any idea about what actually happened and what to do with that. If you have GC logs enabled in advance, you don't have this problem. There is another useful option that JVM provides. It can create the heap dump automatically in case there is a out-of-memory error happened in the application. And I would encourage you to enable this as well. And finally, there are multiple tools available for monitoring JVM, like Visual VM and Flight Recorder. And they have a lot of useful features for monitoring JVM and to like check what issues are happening there and how healthy is the JVM. And I encourage you to get familiar with these tools and use them like in everyday work when you're developing Java applications or when you're creating applications with Apache Ignite, because Apache Ignite is a JVM project. I will also recommend you to check out the documentation page. The link is at the bottom. All these like details I just covered are there as well as all the actual JVM settings that you can use to enable out-of-memory heap dump, for example, to enable GC logs, and also there are sets of settings that we recommend to start with. They're kind of based on our experience of using Apache Ignite. But keep in mind that this is not something that you must use, because every use case has its specifics, and very often you will have to do some additional tuning on your own. All right, so now let's have some fun and do some coding. I'll have a quick demo for you. And I will show you like a couple of features of affinity collocation and how you can use affinity collocation in Ignite to improve the performance. So imagine you have an account object. So this is our data model, very simple. We have an account object which has the balance field, which we will use later. And also there is some payload. So I mean, I just created byte array for simplicity, like a big byte array. But in real use case, it will be like some real data, of course. It will be hundreds of fields, for example, with some data about this account. So let me switch to the first example. So let's imagine we want to read the balance, get the balance for the particular account. So here, in this example, I start the client node. I also, oh, by the way, I'm sorry about that. So I have to start the server node first, of course. Okay. So here, in this example, I will start the client node, create the cache for my account objects. So the key will be just unique ID, and the account will be the value. Then I will create a random key and create a new account with initial balance of 1000 and save this account in the cache. And then I will try to get balance just using simple get operation. So I will get the value to the client node, from the server node to the client node, and get the balance and print it out. And I also have this execute benchmark method, which just runs the provided runnable, measures the time, and prints it out. All right, so let's run it and see what result can we get from this. So this is the client node. We see that there is a server node that we started earlier, and also the client node, which is our current node. And we see that we got 1000 balance, which is correct, but performance is not really good. And mainly this is because the time is pretty big, because we transferred the whole object from the server into the client, which includes this large byte array as well. And here in the second execute benchmark invocation, I will make like the improved version of the same operation. For this, I will create a special closure. I have it already predefined. So let me describe what happened here. So here is the balance getter closure. It's actually an Ignite callable. Ignite callable is just a callable that is also serializable and can be sent across the network. And it returns our double value, which is our balance of the account. And it has the key we want to get the balance for. And we also inject the Ignite instance here. So this is just, I just put the Ignite field here and put the special annotation, and it means that when the closure is executed on a server node, the Ignite instance will be injected to this closure so that I can use the Ignite API within the closure. And inside the closure, I will get the cache from the Ignite, and then get the key, get the value for this particular key that we had here. And then I will get the balance and return only the balance. So this code will be executed on the server side, and the whole value will never be transferred across network. The only thing that will be sent across network is the double value for the balance. So let's change the code here. So we will do basically, we will use compute API. So there's a compute method that gives you the Ignite compute API. And I will do call, I will do the affinity call method. So the affinity call method is actually the special method for running the closure on a particular node where the specified key is stored. So here I have to provide the cache name. I will also provide the key which we are using, and I will provide the create a new balance getter object with this key as well. So what it means is that Ignite will send this balance getter closure to the node where this key for this cache is stored, directly to this node. So this get will be actually a local operation. It will not imply any network round trips. So let's run it again. What? Okay, so as you can see, the difference is pretty big. So it's like orders of magnitude faster when we use affinity colocation, but the balance is still correct, and we got the correct value, but we got it much, much faster. And another quick example, like imagine we want to actually do kind of the same thing, but we also want to update the balance. And here we again created the cache, we started the client node, created a new account, and then we get the key, get the account from the cache, get the old balance, update the balance, like increase it by 2000, and put it back into the cache. So let's run this example. So again, it takes a while because we transfer all this, the whole byte array. And in this case, we do this twice because we not only get the value, but we then return it back. So we, without changing this byte array, we actually transferred it across the network twice, which is not really needed. And another problem here is that this is actually incorrect. It's not only slow, but it's incorrect because if there are two threads doing this concurrently, they will likely get the same value for the current balance, and they will update the account with the same balance as well. So there will be two threads doing this, but the balance will be still like 3000 because they will both update 1000, and the new value will be 3000 for both of them. And in Ignite, there is a special feature that you can use to do this not only on the server node in collocated fashion, but also atomically. And this is called entry processor. So let me show this. So entry processor is actually part of the cache API. And this process method will be called within the entry lock atomically with the cache update. So here we get the argument, which will be our addition to our balance. We will get current account from the entry provided here. We will get old balance. We will update the balance and save the new value here, and then return the old balance back. And this will all happen atomically, so that if there are two threads doing this concurrently, they will not interfere with each other. They will basically do this one after another. And here we will use Cache API. There is a special invoke method which takes the key, an entry processor instance, and the argument in this case I want to provide 2000 so that my balance is increased by 2000. So let's run this version of the code. Oops. What happened? Ah, right. I have to make it double, of course. Sorry about that. Okay, so it's done, and we see that the results are correct. So we had 1000, which was increased on the first in the first operation. So the old balance here is 3000. This is correct, and again the performance is much better. It's again orders of magnitude faster with collocation than without collocation. All right, so that would be it. I'm actually ready for your questions, and I will hand it over to Alisa.
Okay, great. Audience, if you have questions, go ahead and enter them in the questions field in the GoToWebinar control panel. And we have some questions for you already, Val. The first one is, where is the cache stored?
Cache stored, cache is deployed, so it's a distributed cache. So basically, you will have a set of nodes. You can have like a set of physical nodes, and on each physical node, you will run Ignite node. And Ignite node will manage the part of the data that is stored locally. And the cache will be deployed basically on these nodes. You can control this, so you can have the cache be deployed on all server nodes in topology, or you can create kind of a logical cluster groups so that different caches are deployed on different sets of nodes, so that you can have different roles of the nodes. So basically, the cache is stored on the Ignite nodes.
Okay, the next question. Is there any existing implementation of connection pool working with Ignite JDBC? If not, would it be possible to develop one using Apache Common DBCP framework?
Yes, of course. So Ignite provides the JDBC driver, and you can use this JDBC driver with any available pool implementation. So it's compliant with JDBC standard. So if this pool works with JDBC data sources and with JDBC connections, then you can use it for Ignite as well.
Okay, next question.
Including DBCP implementation as well. Yes.
Sorry about that. I noticed that the query performance is worse when using big off-heap memory than launching multiple nodes in the same machine. Is this the case? If this is the case, what is your recommendation and comments between using off-heap memory versus multi-nodes approach?
Well, yes. I mean, in general case of heap memory, I mean, SQL queries can be a little slower on off-heap memory, mostly because the indices are stored in off-heap memory as well, and there are a lot of lookups into off-heap memory which can slow you down. And also, if like the query does a lot of scans, so if you have a large table and you scan this whole table, you may want to start multiple nodes per per box to better utilize the CPU. Because basically, when you execute a query, it's executed in a single-threaded fashion on each node. So each node has one thread executing it. And when you add more nodes, even if they're on single physical box, you have better parallelization of query execution. So I would say that, especially if the query does a lot of scans, if it's kind of analytical query that goes through the whole database and calculates some average, for example, then it's really a good idea to have several nodes per box and use. And in this case, you are free to use on-heap memory for that because basically you don't have the problem of a large heap because it's split across different JVMs. But if it is more like OLTP use case with small easy queries, then I would say test it first. So usually it's the difference is around like 20-30% in many use cases. It's acceptable, and it's better to have this little performance degradation, but do not have all this hassle of deploying multiple nodes per physical box because it's much more difficult from deployment standpoint.
Okay, next question. How do the write-backs happen to a relational database management system, and how can you control them? How can you control how often? What do you recommend the frequency to be for a high-volume, real-time transactional system?
Well, so basically this is done through the cache store interface I mentioned in data loading section. So the cache store is an interface that you can implement to provide the logic of mapping between the objects and the relational database. There is also implementation out of the box, which also actually suits most of the real use cases. But it's highly customizable, so you can always implement your own. And there are two different modes of updating the database. So there is a write-through. In this case, each time you update something in the cache, it will be synchronously update the database as well. And this gives you the guaranteed consistency between cache and the database, which is especially important in the transactional use cases. In the case if you run transaction, we also allow to make sure that the transaction in the database, like the underlying database transaction, is also consistent with the cache transaction. So if something is wrong on the database, cache transaction is rolled back as well, and the other way around. And another option is right behind, which is actually asynchronous update. So if you update something in the cache, this entry will be only stored in the temporary queue first. And then this queue will be automatically flushed eventually into the database. This is much faster from performance standpoint of your update operations, but this is less durable because in some cases, because if the node dies before it flushes the queue, you actually lose these updates and they not end up in the database. And there are several parameters that you can control in right behind around how frequently this flush is happening, how large is the batch, like with data streamers. So you can configure the batch size, the queue size, and you can also configure the timeout after which the queue is flushed anyway, even if it's not full yet.
Okay, we have time for one more question. And everyone else, I'll make sure that Val gets your questions and he'll do a follow-up blog post in the next week or so. Okay, so the last question is, would the cache backup be helpful for query performance? If a node with primary copy is down, would the backup be upgraded to primary and serve for queries?
Yes, it will. So the answer is yes. So if you have a backup copy and the primary copy dies, disappears from the cache, the backup copy will be promoted to primary, and in the background there will be a rebalancing process which will create another backup copy, so that if you lose primary once more, you don't lose the data. But it doesn't actually affect performance. Actually, if you lose nodes and if topology changes and there is the rebalancing in background, you will most likely have performance degradation, like temporary degradation. But the having a backup copy does not affect performance, but it gives you the durability of your data.
Okay, well, this brings us to the top of the hour. Audience, I want to thank you so much for your participation. And Val, thank you for a great job. Everyone, please note that I will send a copy of both the recording and the slides within 48 hours. I typically do it much quicker than that. And with that said, thank you so much. And Val, hope to see you again on another webinar soon.
Yeah, thank you everyone for listening, and goodbye.